All right, should we start now? All right, should we start, Mehdi? Anusha? Okay, okay, let's start then. All right. Mehdi, quick question. If we shift the class by 12 hours, let Anusha also come, then we will discuss this. I feel that if we shift it to morning in India and evening in US, I think that would suit most of you. I think I'll just drop all of you in an email and then you can discuss. Okay. All right. Great. Great. Okay. Okay. And in that's in IST. Okay. All right. No worries. Yeah. All right. So before we talk about anything, let's first understand what does it mean by scaling out or scaling up. All right. So there are two different terms for the same thing. So I'll just be very, very clear on the terms. This is called scale up. Okay. And this is called scale out. Okay. All right. So if you have a cart and you want to carry more goods and your horse is not sufficing, then if you replace the horse with the elephant, this is called scaling up or vertical scaling. And this is the general traditional way of doing the things before newer kind of carts were available. Okay. Now, if you replace a horse with a new kind of first you replace the cart with new kind of cart which can support multiple horses, then this is called horizontal scaling. Okay, or if you have 4 horses in the cart and you want to add 2 more horses, then that is also known as scaling out or horizontally scaling. So this behavior, this what do you call these are the two different approaches. While vertical scaling cannot go beyond a certain point. Now, uh, let me take the computing example. Let's say you are facing a lot of traffic or lot of load on your database server. Increasing its memory or increasing its CPU to multiple cores and try to do all kind of um, increasing its speed and adding more RAM and putting the hard disk, bigger hard disk, faster hard disk. So that is called vertical scaling. But if you create multiple servers and you try to balance the load of these one machine by instead of one machine, you are getting the things done by multiple machines parallelly. This mechanism is called horizontally scaling or scaling out. Now, the second mechanism of where you have multiple machines doing the things is far more scalable. It is far more scalable. While the first approach, the vertical scaling approach, does not scale well. After a point of time, you will realize that your elephant is not sufficient. Okay, and then you will say that what should to do now? Okay, should we wait for elephants to grow big? Or we say that it's not possible to carry that kind of load. Okay, so that is the reason why the whole idea about distributed computing or horizontal scaling came into play. All right, now we have, okay, so that was a quick overview of scaling out and scaling up. Now, you must have heard a lot about what is NoSQL and all that stories. So we will just go through a quick story on 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 the NoSQLs, and then that will make a lot of more sense to you. Okay, so in simple words, when you hear that people are using moving to NoSQL, the first question you will ask that why? What's the point of having this new genre of databases? Okay, so there are three reasons. First, to store big data. Second, make it highly available. Meaning, if you think about a scale of Facebook or scale of Amazon, there are thousands of users accessing the website per milliseconds, right? Now, to make your website so highly scalable, your database has to be that kind of available. Okay, because whole load of various servers actually ends up on the database. Now, if your database is not that available, as in if your database cannot handle so many requests per millisecond, then it cannot. And also, if you are just looking for keywords, keep in mind that there is a word called TPS, transaction per second. So that's also it's a significant metrics for measuring availability. Okay, so your database has to be highly available. It should produce a lot of TPS, transaction per second. It should be able to handle lots of TPS and scale out. Today you have 1,000 users. Tomorrow, if you have 10,000 users, can you can you just by adding 10 times machine, can you handle that kind of load? So that is called scale out architecture. An architecture which can be expanded, which can be easily increased. So so that's called scale out architecture. And in all these three cases, the traditional databases do not suffice. Okay? Traditional databases, even if they store a terabyte of data, but if you have to read the data, scan the data, it's impossible. You are limited by the disk IOs, the rate at which the hard disk can read the data. Now, in case of high availability, okay, so if you have many concurrent users, actually both of these systems, NoSQLs, MySQL, Oracle, Postgres, they are limited by the memory of the machines, because the more number of connections is a function of how big the RAM the database has. Okay, so therefore they are limited excessively because of the hardware constraints as well as their architecture. Third is they they cannot scale out, meaning the database has to run on the same machine. If and you will understand the reason. I'll go through the case study before going into more theory, and that'll give you a very good idea. So it's a interesting story, and this story has happened with many companies. Many companies who were born in the internet era. In today's era, where you launch a service, you have couple of press releases, you have couple of requests coming in. After a point in time, you hit the roadblock. Okay, so let's hear the story. So the team was very happy. They did a initial public launch and champagnes, and then you have this. They moved the data from local workstation to shared, and everybody was happy. And so so they remotely hosted MySQL instance with the well-defined schema. All right. So so you were pretty happy on this day, but after some time, your service was really useful, and it became popular. You started with your friends and families, but after some time it got popular. Too many reads started hitting the database. Too many reads started hitting the database. So you realize that why don't we just cache the data? Okay, it's a very common phenomena that for every request, if you have to go to the database, so if you have to go to the database quickly, uh, every time the request is coming, it's unnecessary waste of time. If you could just scatter it from the memory, from the RAM, it'll be very faster. So a system like memcached, which caches the database data, you you add that kind of servers, and whatever the common requests are there, we start caching those. It's a common, if you are from software development management, you will know that the caching is the first knee-jerk reaction. So service became popular, so you realize that lots of requests are directly going to database. Instead of letting them reach to the database, the common request, you have cached it in memcached and let memcached serve it. Let the web server read from the memcached instead of the database. Now that gave you a little breather on the database part. Now, after some time, you did some kind of PR and some kind of more advertising. The service continues to grow in popularity. Now, after some time, too many writes start hitting the database. It's an actual story. I have faced this situation with my data at the one of my employers. So so too many writes start hitting the database. Okay. Now, so what you do is, this is the common IT guys do this kind of thing, and I think this is a very reasonable step at this point of time, or at that point of time when there were no NoSQLs. We Since the service is continuously growing in popularity, the chances are you got some VC money, and using the VC money, or you raise some fund, you put that money into scaling up the server. You buy really expensive server available in the market for the database. So all you do is you beef up the server with 16 cores, and 128 GB RAM, and you buy really expensive hard drives with 15,000 RPM. Nowadays, the hard drives are really faster than this one, so we can buy a faster hard drives. As well as we bought 200 gigabytes of RAM instead of 128 RAM, and put more cores. Okay, now uh, we just put lots and lot of money into the database. Okay, because we did not know a better solution. But again, as the new features, so at this point you were pretty happy, you solved your problem, bingo, and now you are seeing that everything is just smooth. Let's just hire a couple of product managers and add more and more features. Now, eh, if you think in terms of, let's say, Amazon. At Amazon, why I'm using Amazon, because not many people would be aware of the smaller uh, e-commerce like Flipkart or something. So at Amazon, if you think about the product detail page, you will see so many features. Like there are ratings, there are reviews, there are recommendations, there are title, there are authors on a book. Then you have these images. Sometimes somebody came up with a new cool idea called show the video as well in the product image. And then somebody else came up with the idea, let's just ask people to to ask a question to other people. So as and when you felt like expanding, you started adding more and more feature, and every feature you add, it's actually creating another table in the database and having a referential integrity saying product ID and then right review and the review and so on. So every feature you add will create a new table of its own, and then when you have to serve the whole page, you have to join all these tables. More the features, more the joins, right? And that's like classic case of of any website. So after some time, you realize that there are too many joins. Now there are two things have happened so far. First, First thing that have happened is you added memcached, which is a caching. When you put something in cache, as in memory, instead. So what happens is every time the data changes, you update the cache, and this there is always a time lag between the change in the data, actual change, and the cache being reflected. So during the time the cache is stale, it's actually serving the data, serving to the customer, which means customers are getting the wrong data, which is horrible. If you are a DBA, if you have met the DBAs, for them it's a horror. It's inconsistency, right? This kind of situation is called inconsistent. So first thing we have done in order to accommodate so many requests is made our data partly inconsistent. Okay. Now second thing, when we have lots of features, we start denormalizing. What does it mean by denormalizing? We start pushing all the tables into a single table. Instead of having separate tables for each feature, we start trying to combine it. Instead of having the product description as a separate table and then put the referential integrity, we start pushing it into the same table, or we start copying the data at two places. Now, the moment a DBA hears this, okay, he will have really irritating time, because that's not what he was told in DBA school. The first thing we were told while learning databases is normalize, right? And apply the chord theorem. Now, and and just because you are under the pressure of performance, you are forced to you are forced to denormalize the data. So the second property we had to forego. First property we had foregone is the consistency. The second property we are foregoing is the normalization. And when you have no normalization, the referential integrity does not make much sense. So we have let go of referential integrity. Now, the service is still rising in popularity and server is heavily swamped with the number of requests. Things are get too slow. So what you do is you stop doing a lot of things on the database side. And these are very important aspect. Keep when you see a story like this, you should feel that it is the time to go to NoSQL. Now, if you stop doing at this point of time when you realize the database is still swamped, let's try to stop all the server side operations. Let's stop all the database side operations. Okay. Now, what do we mean by database side operations? Things like pre-compute, things like stored procedures, things like triggers, things like triggers, stored procedures, and the queries where we are trying to do a lot of computation on the server side. Let it be done on the client side. Now, after doing these kind of optimization, still the queries will be slow. So what we start doing is periodically pre-materializing. Okay, most of the complex query, if you realize that hey, every time this query comes, we have to do a lot of work, and this query cannot wait. Our user, if user is waiting when the for the first time they're hitting our website, it's a shame. Therefore, what we used to do, even at Amazon, we did a lot of such optimization even today at various levels. Okay, so even today, when when the when the request comes from the user, we pre-materialize a lot of things. Meaning we pre-prepare that okay, these are the things which our user is going to ask. Let's just pre-prepare before user even asks for it. Okay, so, and we keep on doing that periodically. Every morning we have new pre-metallized data, and periodically we keep on refreshing this pre-metallized data. And whenever you have this pre-metallizing thing, it's equivalent of caching. Just that in case of caching, the cache is prepared on demand. In pre-metallizing, the cache is prepared upfront. Okay, so after some time, the reads will be okay, but then writes will get slower and slower. So, what you do, you start dropping the secondary indexes and triggers as well. So we let go of everything which database had to provide, except for data in and data out. We let go of secondary indexes, or we let go of triggers, we let go of stored procedures, we let go of referential integrity, and we let go of the consistency. Now, if somebody is from database background, he will feel as if, what is the point of having a database then? The answer is data in and data out, nothing more than that. Okay, and that's where people realize that databases pose a lot of burden. Okay, we don't need in case of handling a humongous traffic. We cannot afford to have these kind of heavy machinery in the backend, and also we cannot scale out these databases. So that's when people said that let's go with NoSQLs. I hope I'm able to convince you for NoSQLs. All right, let's understand few more ideas behind NoSQLs. This is very important. No matter from what background are you, these are the things which are probably very important, because as of today, every organization have humongous data. No organization can afford to stay agnostic of the B2C as in business to consumer. No organization can afford to skip the data collection. Therefore, Every organization from time to time for various kinds of requirement will have to move in to the databases, to the systems which can handle huge data. All right. Now, there are few things. One is the CAP theorem. CAP theorem says out of three things, C, A, P, C for consistency, A for availability, and P for partition tolerance, you cannot have more than two. Okay, you cannot have all the three. No matter what database you design, no matter how do you design it, you cannot have all the three. You cannot have C, A, and P, all the three. And let's first understand what do we mean by C. C for consistency, meaning all the nodes are seeing the same data at the same time. If you just wrote the data and you are reading just after a microsecond, you should get exactly same data. That is consistency. If you just wrote the data and another user who is reading after a microsecond or a nanosecond, if he gets the older data, that's not consistency. Second, availability. How many requests, how many TPS can your server respond to without failing to give the response? And when I say response, response can be error or success. Okay, but the request need to be catered. So that's what I meant by the request. So a guarantee that every request, that the maximum number of requests gets response. Okay, by the way, not all, there is no absolute availability, meaning there is no server in the world which can guarantee that every request will get answered. There are only guarantees, like we are providing maximum guarantee of delivery of the request. Okay, delivery of the request response. Third is the partition tolerance. Partition tolerance means in case some of your machines go down. Partition tolerance is in partitioning of your network. What does it mean by partitioning of the network? In case your network has some nodes that are going down, or some nodes that are getting disconnected from rest of the nodes, that's partitioning. How much partition tolerant is your system? So 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 no system in the world can guarantee the partition tolerant along with other systems. Okay, other properties. So these are the three things. All right, are you audible now? Am I audible now? So till what point was I audible, Sahab? All right. All right. Yes. Sahab, can you hear me now? All right. So coming back to the question, say, so we had three CAP. Out of these three, no system can guarantee all the three. Therefore, you need to. Therefore, therefore, you need not worry. Okay. So even if we are going for NoSQL or we are staying with RDBMS, none of these can answer to these all the three requirements. I'll give you a diagrammatic way of representation. It has taken me some amount of time to to present it this way. Okay. All right. Now there are these three kinds of systems which I've tried to depict in these diagrams. Okay. So what is it that I'm trying to depict here is There are three kinds of architecture. The first architecture on the leftmost, this one, is our typical relational database. This is our typical relational database. And here also, okay, let me just give me a second. Let me update this diagram. This is a little old. This is okay. All right, all right. So yeah, on the left hand side, you see this database, which is your relational database. This is your relational database. And in this database, all the users are reading and writing from the same machine, which means that if this user writes something and another user tries to read the same thing just after a nanosecond, he will see the latest data. It is strongly consistent. In case, in case there are too many requests that are coming to this server, those requests may not be catered by this machine because of the physical limitation. Therefore, it's not highly available. Now, in case this machine goes down, nobody gets answered, neither the readers nor the writers. Nobody gets any answer. Therefore, it's not partition tolerant. Second is another architecture where you have A and B, you have A and B, okay? You have A and B. All the readers are reading from B while all the writers are writing to A. And when the user writes, one of the user is updating a record or deleting a record, that information is transferred through over the network to B and B update itself. Now you would notice that by the time the change reaches from A to B, by the time the change reaches from A to B, there might be some users who are reading from B, and those users would be reading the stale data because it's taking the time. It is taking the time for some change to be reflected from A to B, and therefore, all right, therefore, it's not consistent. It's not strongly consistent. It is eventually consistent. Although we know that after a point of time, the change is going to reach from A to B and things are going to be okay. There won't be any conflicts because there's nobody else who is writing at B. Reading is happening from B, writing is only happening from to A, and data is only coming from one direction. Therefore, we know that it's going to be eventually consistent, and most of the NoSQLs actually lie in this domain. They say that, okay, we are not strongly consistent, but we are eventually consistent. All right. The third kind of databases are this one, where you have A, which is primary and the kind of a main single point of contact, while there is a backup server called B. So all the users are writing to A and A is transferring the data to B as a backup. Now, while it's consistent in the sense that all the users are reading from A and writing to A, but it is not really available because A is highly precious resource and all the users are talking to only A. We cannot increase the number of requests after a point of time. So it's not available. But it's partition tolerant. In case A goes down, we can replace A with B. In case B goes down, it doesn't matter. So it's fairly partition tolerant. All right. So that was the cap theorem. Cap theorem says that as you saw in these three architectures, out of C, A, and P, things are not consistent. All right. So out of C, A, and P, none of the databases can guarantee all the three. All right. So this part we have already discussed. So I'll just drag it a little bit. So keep these things in mind. Although NoSQLs provide you a great deal of storage, great availability, but they fail to provide you a strong consistency. All right. So HBase is one of the databases, and also you can see in this diagram, you can see that nobody lies in the center of this diagram, while there are many players in the intersection of C and P, C and A, and P and A. Okay. Although this category here, RDBMS generally lie in the consistency domain, not in availability and consistency. All right. Now, HBase is one kind of database which is not highly available but is consistent and partition tolerant. Consistent and partition tolerant because it follows a slightly this kind of model where there is somebody called HBase master, which is a single point of contact, and then there is a backup for the HBase master, and uh, rest are reason servers. So there is HBase master. All the users who are writing or reading talk to the master, and then master writes to the region server. So initially, uh, in case of HBase, you have tables, you have rows, and you write to the rows, as well as you can add as many columns as you want. Okay, so in the difference between HBase and relational databases is in relational databases you define a table. Here you don't define a table in terms of columns and their data types. Here you just say that this table is composed of groups of columns, not columns, but groups of columns. You just give them the name. That's it. That this table will have only one group of column called column family, and this group, the column family name is CF1 or my something. So in case of HBase, you have tables, and tables have column family, and column family inside column family you can add as many columns as you want, and as many columns as and when you want. Okay, you can keep on adding more and more columns from time to time into the column families. Okay, now when you have a table like this, so in this architecture you see there is somebody called master, there is somebody called region servers. These regions, there are multiple region servers running on same yarn on the same yarn cluster. So the region servers are running inside the containers on each node manager. Okay, so those region servers are running inside those containers on the same yarn cluster. So whenever you have to write to a table, you have to say insert a record, update a record, or insert a column, delete a column, update a column. All of this happens through the master. So you inform the master, master informs the region server. In case you are writing lot of data to the region servers, in those cases, master connects you to the region server. Okay, so interesting part is that initially when you create a table, there'll be only single reason server. There'll be only single reason. So region servers are actually machines. These region servers store subsets of the rows. A big table is broken down into parts and is stored on these region servers. And again, region servers store data in HDFS. Therefore, each section of the data is going to be copied and kept backup by HDFS. So master stores the data on region servers and re- and and initially there is only a single reason of the table. The whole table is a reason, and then as and when more and more rows you get inserting into the table, it is split into two equal parts, and those two equal parts move to different reason servers, and then again more inserts will happen, and then regions will keep on increasing, and after a point of time when these regions increase beyond a size, they are again broken down into parts. So this keeps on happening all the time. Okay, this keeps on happening all the time as more and more region servers are more and more records are being added. So you can see that exactly same way we had HDFS, here also the architecture is same. A table is distributed into sections and put it on multiple servers so that when the request for data comes in, master exactly knows what are you looking for, and it can send your request to accordingly to the corresponding region server. Okay, again, every record in HBase, every row in HBase is marked with a unique identifier which you will have to specify. Every row is supposed to have a primary unique key. Okay, based on that, and based on that the data is ordered based on the primary unique key. All right, now moving ahead, so that was about the HBase architecture we have talked. So is the HBase clear to you? All right, so Mehndi Sahab and Anusha, were you able to use the hue? Were you able to create your folder, upload some data? All right. Make sure that you go through the HDFS, browse the HDFS, understand, and also check Ambari. Also try to understand how do the things work. All right. All right. So that was our discussion on HBase architecture. So that's about HBase. Now, when you want to read data from HBase, you are only allowed to do get and put. You can insert a row, update a row, delete a row, but in terms of very rudimentary way. Okay, in a very rudimentary way. I will try to execute some of the commands which we have discussed today. Just give me a second. Let me. Since the cluster had changed, so the commands have a bit changed. All right. Now I like to show you the. All right. Let me try to take this. How many of you are aware of Unix? Anybody? I think Mehdi is comfortable with Unix. What about you, Sahib? Have you used Unix before? All right. All right. Never mind. You will learn slowly. And all right. I think Anusha is not in. Okay. Okay. So where is the. All right. I will try to run one of the Mapreduce and then we will test. Okay. So you can go to the console here and you could log in using the login password which have been provided to you. All right. And then inside here, this command which I have put in. So this command says that here is my Hadoop jar, which is Hadoop streaming. This is whenever you have to do streaming, this is common for you. And this is my input folder. This is where I have stored the data. And what is there in this folder? Let me show you. Okay, let me show you. If you go to say Hue is the way you interact with all these components. Now, when you go into Hue, you will see file browser. Okay, you go to this particular folder, whatever we have mentioned here. That in that folder, you can see inside data, inside MR, inside word count, we have input folder. Inside that, we have this big.txt. It's a big file. You can see that. You can see it's a big file. I have basically combined together all the Sherlock Holmes books and concatenating them into a single file. Okay, so we have got this big file, and that's what we are trying to run right now. We are saying input equals to this, output equals to this. This is the folder where I want to store my data. I can simply say my data and it'll create my folder in HDFS. Please note that this is HDFS. Okay, this is HDFS. We are talking to HDFS from the browser. Okay, so we can upload data to HDFS directly. It will be broken down into blocks and all that magic will happen in the behind the screens. And now when we take this data and try to run this command in the background, it's going to run on multiple machines. But since it's just a single machine right now, it won't do anything much. Okay, so let me just put this command here. So you can see I'm saying here, instead of writing this, we are saying inside the folder called asgiri, there is a folder called word count. We will put the data inside that. Okay, so let's try to say run whatever we have explained today from the console. This console is where the magic is happening. So it's saying that input command is not found. Why? Because it's in another line. So you have to bring full command into a single line. Okay? Although you could put backslashes and get it executed. Alright, now we are trying to run a Mapreduce command. Ideally, you would not need it. You will generally use it says that the output folder exists. This folder, where we are trying to store the data, is already existing. If I click on home, this is my home folder. If I specify a path without slash, it means I'm providing the relative path to the home. Okay, so you can see here there'll be you can see that, right? Here I'm inside asgiri. There was asgiri folders, right? uh, oh, I was already inside asgiri. Okay, so here you can see word count output unix. This is already there, that's why it's giving an error. Let's just delete all these three. Okay, ouch. I think instead of deleting, all right, because our Hadoop command is trying to create an output folder, and before it starts the job, it checks whether output folder already exists or not. So it's starting the map reduce process. What does it say? It says that the command does not exist probably. Okay, so let's try to modify it a bit. Oh, this is correct only. All right, so maybe now you saw something. So mapper failed somewhere. It said this map underscore 001 has failed, so it executed the same command on some other machine. Okay, for whatever reason it failed at that point of time. Maybe it's running a low memory, it's running something else. So that's why it has started the work on somebody somewhere else. Now this is the magic. You're lucky to see this situation where the data did not get uh, the work did not get done at this point. So, but it got done on another machine. So I just ran this stream job. You can see it says succeeded. Although if you see tasks, it says that it started three tasks. Okay, and there was one attempt. This attempt. Okay, this was the attempt of the whole job, and in, inside this attempt there were three tasks: task 0, task 1. There are two tasks for map and one task for reduce. Okay, and when you look at this task, you can see that two attempts have failed, last one has succeeded. Okay, you can see here that the attempts on 54 has failed while 91 have succeeded. Okay, the IP address. So what am I trying to say is that the things which we discussed about task tracker, job tracker, this is the magic that's happening right now. Okay, so you can see the logs, what exactly happened. Okay, it says that the run command has exited and insufficient memory. You can see insufficient memory. All right, great. So, all right, then see you tomorrow and have a great day. All right. Sahab, were you able to see what we discussed? All right. All right, Anusha. Anusha, if you have done the recording, could you just upload it somewhere on YouTube or somewhere in a private mode? And then we will download from there. You can delete afterwards. Hi, Anusha. As we exit the session, it will ask you to convert and then, okay, so convert that recording and send it. All right. Bye bye. Thank you very much. Have a great day.